The word adversarial in generative adversarial networks means that the two networks, the generator and the discriminator, are in a competition with each other. To understand this kind of competition mathematically, we rely on game theory. Game theory is a branch of applied math that was founded by John von Neumann and later significantly extended by John Nash. Game theory can be used to model cooperation and conflict between rational agents in any situation, where each agent can choose from some set of actions, and the choice of actions determines a well-defined payoff for each player. Let's take the game of rock, paper, scissors as an example. Each player can choose whether to play rock, paper, or scissors. That defines a set of possible actions. Each player also has a payoff. Let's say that the winning player receives a payoff of 1, and the losing player receives a payoff of -1. Rock smashes scissors, scissors cut paper, paper covers rock. It's also possible for the two players to tie if they both play the same move. Then both receive a payoff of 0. Suppose that player 1 always plays scissors and player 2 always plays rock. Then player 1 always loses and receives a payoff of -1. This means player 1 could improve by changing their strategy, for example, to play paper more often. What happens if we adapt each player's strategy over the course of several games? If the players are allowed to randomize their moves, they will eventually reach an equilibrium where each player chooses their actions uniformly at random. An equilibrium is an important situation in game theory, where neither player can improve their payoff by changing their own strategy, assuming the other player's strategy stays the same. In the rock, paper, scissors example, let's look at player 1's options, assuming that player 2 chooses rock, paper, or scissors uniformly at random. Let's consider what happens if player 1 increases the amount of times they play rock. 1/3 of the time, player 2 will play rock as well. That results in a tie where neither player gets any points. 1/3 of the time, player 2 will play paper, so the increased amount of times that player 1 plays rock will result in player 1 losing. Finally, 1/3 of the time, player 2 will play scissors, so the extra times that player 1 plays rock will give player 1 some wins that exactly cancel out their losses from earlier. Overall, player 1 got nothing from changing their strategy. We can make the same argument if we think about player 2, since the payoffs are symmetrical. This equilibrium, where both players choose their actions uniformly at random, is an important defining characteristic of the rock, paper, scissors game. We can analyze the game and conclude that rational agents will learn to play completely at random. To understand GANs, we need to think about how payoffs and equilibria work in the context of machine learning. If we can identify an equilibrium in the GAN game, we can use that equilibrium as a defining characteristic to understand that game. Most machine learning models we have seen so far are based on optimization. We write down some model parameters, we write down a cost function of those parameters, and we minimize the cost. In this graph, we represent the parameters with the two horizontal axes. The cost function is plotted along the vertical axis. The goal of the learning algorithm is to find a very low value of the cost function. Usually we don't actually find a global minimum, or even a local minimum. We get stuck in a place where numerical problems make it difficult to keep going downhill. But the optimization algorithm more or less does a good job of finding a point with very low cost. GANs are different because now there are two different players, the generator and the discriminator. Each player has its own cost. In one easy-to-visualize version of GANs, the cost for the discriminator is just the negative of the cost for the generator. In this simple case, we can describe the whole game using a value function. The generator wants to minimize the value function, and the discriminator wants to maximize the value function. Recall that earlier we said an equilibrium occurs when neither player can improve their situation without changing the other player's strategy. That happens when we are at a maximum for the discriminator and a minimum for the generator. This kind of point is a saddle point. You can see here that the game plotted here has an equilibrium in the middle. One of the horizontal axes corresponds to the parameters of the generator. If we take a cross-section along this axis, corresponding to the parameters of the generator, the equilibrium looks like a minimum of the value function. The other horizontal axis, perpendicular to the first, represents the parameters of the discriminator. If we take a cross-section along this axis, the equilibrium looks like a maximum of the value function. This gives us a good way to understand games played by deep nets. We want to find a point in the space of both players' parameters that is simultaneously a local minimum for each player's cost with respect to that player's parameters. If we analyze the game for GANs, the local maximum for the discriminator occurs when the discriminator accurately estimates the probability that the input is real rather than fake. This probability is given by the ratio between the data density at the input and the sum of both the data density and the model density induced by the generator at the input. We can think of this ratio as measuring how much probability mass in an area comes from the data rather than from the generator. If we use the mathematical tools provided by game theory, we can show that if both networks are big enough, then there is an equilibrium where the generator density is equal to the true data density, and the discriminator outputs 1/2 everywhere. Unfortunately, even though the equilibrium exists, we may not be able to find it. We usually train GANs by running 2 optimization algorithms simultaneously, each minimizing one player's cost with respect to that player's parameters. Unfortunately, these optimization algorithms do not necessarily find the equilibrium of a game. A common failure case for GANs is that when the data contains multiple clusters, the generator will learn to generate one cluster, then the discriminator will learn to reject that cluster as being fake, then the generator will learn to generate a different cluster, and so on. We would prefer to have an algorithm that reliably finds the equilibrium where the generator samples from all the clusters simultaneously. That is a key research problem concerning GANs, designing a learning algorithm for finding the equilibrium of a game involving high-dimensional, continuous, non-convex cost functions. Hopefully some of you will have ideas for how to solve it and unlock new applications that require very reliable learning algorithms.